In this lecture, we shall discuss conservative and non-conservative forces, conservation of mechanical energy, and work done by an external force when friction is involved. So let first we discuss about conservative and non-conservative forces. Okay, the primary test for determining whether a force is conservative or non-conservative is this. Let the force act on a particle that moves along any closed path we see here, beginning at some initial position A and eventually returning to that position so that the particle makes a round trip beginning and ending at the initial position. The force is conservative only if the total energy it transfers to and from the particle during the round trip along this and any other closed path is zero. In other words, the net work done by a conservative force on a particle moving around any closed path is zero. So if the force acts on the system and starts from point A and goes along this path and comes back to the initial state by this path, so the total work done by the force for this closed path will be zero. So a force is conservative if the net work done by a conservative force on a particle moving around any closed path is zero. So we understand this condition is for the conservative force. Let's suppose this is part 1 and this is part 2. Let's suppose that a particle moves from point A to point B, along either path 1 or path 2. Okay, this one is closed path A to B and then comes back from B to A, but if we draw it, okay, here we say the force acts on the particle and state has been changed and along this path, and if the force acts on the particle and this time it goes to state B along this path 2. Then for a conservative force, work done from A to B along path 1 must be equal to work done from A to B along path 2. Where the subscripts AB indicates the initial and final points respectively, and the subscripts 1 and 2 indicate path. And if this does not happen, then we say that the force is non-conservative. This result is powerful because it allows us to simplify difficult problems in physics when only a conservative force is involved. Let us suppose that you need to calculate the work done by a conservative force along a given path between 2 points, and the calculation is difficult or even impossible without additional information. We can find the work by substituting some other path between those two endpoints for which the calculation is easier and possible. Okay, let us now discuss about the conservation of mechanical energy. If K is the kinetic energy, and U is the potential energy, we know the mechanical energy is the sum of kinetic energy and potential energy. So the mechanical energy is K plus V. Now if we take changes on both sides, that means therefore delta E mech equal to delta K plus delta E. These are changes. Change in mechanical energy this is change in delta K kinetic energy, change in kinetic energy, and this one change in potential energy. And the conservation of mechanical energy tells us that the change in mechanical energy must be zero. Or the change in total mechanical energy of a system must be zero. That means delta E mech equal to 0, which means delta K plus delta U is 0. And what is change in kinetic energy? This is Kf minus Ki, and this is Uf minus Ui, equal to 0, where Ki is the initial kinetic energy, K final kinetic energy, Ui initial potential energy, Ua final potential energy. From this we can write down Qf minus Ki equal to minus Uf minus Ui which can be written as K plus Ua equal to Ki plus Ui. That means total mechanical energy is constant. You see the total mechanical energy in final total mechanical energy is equal to initial total mechanical energy. I indicates initial, F indicates final. So from this we can say that in an isolated system, where only conservative forces cause energy changes, the kinetic energy and potential energy okay, in an isolated system where only conservative forces cause energy changes, the kinetic energy and potential energy can change, but there's some the mechanical energy of this system cannot change. So the individual, kinetic energy and potential energy of the system can change. but the total mechanical energy does not change. This is the principle of conservation of mechanical energy. Mathematically, we can say delta E mech equal to delta K plus delta U equal to 0. Okay, next we consider work done on a system by an external force when friction is involved. This is the last topic of this part of chapter 1. Okay, let us suppose that body of mass m moves to this position and initial velocity say was v naught and final velocity v, and the distance is d, and there is a friction. Okay, let us suppose that we have this is the surface on which the body moves. Okay, there will be a frictional force which will act opposite to the applied force F. We call it small f k, kinetic force of kinetic friction. So the net force. Okay, we shall find out an expression for the work done by an external force capital F when friction is involved. Okay, net force on the particle so net force will be F minus Fk, and this will be mass into acceleration. A is acceleration constant. Let us suppose that this is constant force capital F, so the acceleration is also constant. And d is the displacement, v naught is the initial velocity. For simplicity we consider one-dimensional case. The final velocity. Frictional force. F is the applied force. Now we know for constant acceleration or constant force equation of motion is we know v square equal to v naught square plus twice a, and we have the displacement d. And from this we can find the acceleration. So this acceleration here will be substituted here. So this is v square minus v naught square divided by twice d. So we substitute 2 into 1, we get W equal to I'm sorry F minus Fk equal to mass into acceleration ma, and a is this. So we substitute here, so we can write down this. Therefore work done by the external force F, we assume constant force. So is W equal to, we know, force into this. So is but what we see from this expression that this is the change in kinetic energy. So we can write down this is delta K and this is FD into D. FK, I'm sorry, this is FK, not FD, this is FK. This is the expression for the work done by an external force F when friction is involved. This delta K is the change in kinetic energy. Half mv square minus half mv naught square. If we had, let's say this is equation 3, change in potential energy, during the work done, then the work done W would be replaced by then 4, not 3, this is 3, and this is the total change in total mechanical energy, says delta E mech plus this Fk2d. Now this work done by this frictional force Fk into d actually would produce heat on the surface on which the particle slides, and also the particle, the work done by the frictional force is Fk into d, which will produce heat on the body and the surface on which the body slides. Body means the particle. Let this change in thermal energy of this system, the particle and the surface, be delta E thermal, then this one we can write down this, and the total work done would be written as this equation 5, which is the energy statement for the work done on a system by an external force when friction is involved. So this is the end of the part 2 of chapter 1. In the next lecture we shall consider the last part of chapter 1, that is collisions.